welcome to the Ceramics Restorations Key for Success webinar. It is being presented by Dr. George Tysowski, and we will begin the webinar shortly. And now I'll turn the reins over to Dennis Urban, CDT, Director of Clinical Education. He will be introducing tonight's guest. Please feel free to reach out to him with any questions or comments around what you would like to learn about in the future. Thank you so much, and take it away, Dennis.
Okay, thank you, Jessica. Thank you, everybody. Thank you for joining us tonight. You're in for a treat. This is going to be a great webinar, as all the Dr. Tysowski's webinars have been. So you're in for a treat tonight. But to give you a little background on Dr. Tysowski, DDS, MPH, and FACD. He's the head of global training and education and senior vice president of technology and professional relations for Ivoclar Evident. In this capacity, Dr. Tysowski is responsible for research and development and education activities for the North American operations for Ivoclar Evident. And his primary emphasis is on the integration of new technologies into the dental field. He serves as an adjunct faculty member at SUNY at Buffalo School of Dental Medicine and the Eastman Dental Center at the University of Rochester. And Dr. Tysowski is a fellow of the American College of Dentistry and the Greater New York Academy of Prosthodontics. He's also an honorary member of the American College of Prosthodontics and has served as a board member of the Academy of General Dentistry Foundation, the American Academy of Cosmetic Dentistry, and the American College of Prosthodontics Foundation. He has also served as a chairman of the board for the Oral Health America Foundation. And Dr. Tysowski earned his DDS degree from the University of Minnesota School of Dentistry and has a Master's of Public Health from Minnesota School of Public Health. With that, I'd like to welcome Dr. Tysowski. Thank you for joining us tonight, and we really appreciate you being here.
Well, thanks, Dennis. A real pleasure to be here, and greetings, everybody, and a real special thank you for NDX DSG for the invitation today. Really look forward to a stimulating session, I hope, for the audience here. We're going to be covering ceramic restorations, key for success. Just before I start, I just want to provide a disclosure. Obviously, I'm here to educate on technical matters relative to new all ceramics, but I am employed by Ivoclar. So there might be some mentioning of products that I'm related to my research activity, but my primary emphasis, of course, is on education on technical aspects of the profession. So ceramic restorations, key for success. We're certainly in a very strong new contemporary development pattern of new materials, new techniques, new procedures. And relative to my outline for tonight's activities, I'll provide an overview of digital technology, material selections, proper tooth preparation design, cementation protocols, finishing and polishing of these aesthetic restorations, and professional care and maintenance. On digital technology, we're really going through a renaissance of new activities and new material developments. And what's changed is typically we focused on developing new materials. However, the processes have changed so radically with chairside scanning, milling, interlaboratory communication of sending cases out, designing them accordingly. We have a whole new renaissance of new developments of techniques. And certainly we've moved from the traditional casting or pressing technologies, where today we have modern milling machines, again, both at chairside in the laboratory setting. As you can see here, some of the new elements of design. Here we have modern laboratory milling machines that can mill zirconia, where we have the pre-sintered pucks as far as unsintered pucks accordingly. We also have blocks of glass ceramics that can be milled for final restorations, providing high quality results for us in a variety of different settings. Secondarily, that we could communicate now with laboratories either through traditional analog impressions like polyvinyl siloxane, or obviously with the new scanning methods that we have with a variety of techniques where we rival the accuracy of traditional impressions with digital files that we can send to the laboratories and design accordingly. Here we see as far as chairside applications where we have single processed restorations, either in zirconia or also in chairside lithium disilicate type of restorations for proper fabrication. So as we move forward, there's a boom today of number one, either having full access to digital technology or providing a resource where we basically scan and send the restorations and data according to our laboratories, where we can work with them with their expertise of providing design capabilities and fabricating these restorations accordingly. So scan and mill is one option chairside, but what is growing at a much more rapid pace today is scan and send. the ability of taking chairside scanners, capturing the images, and then sending them off to your laboratory for design and fabrication. The accuracy of these units have tremendously improved, and really from the rivalry as far as the different areas. Here's a study from a university in Turkey recently published in the JPD. And if you can see in the middle there, we see scan R relative to the area. Some of the new scanning methods provide very high accuracy, basically in the low teens to even single digits of accuracy of these restorations. And some of the newer scanners are coming out, maybe not as accurate, but 60 microns below, but 10, 11, 16, 9 are very accurate figures that provide a very significant result to quality restorations and delivery by the laboratory partnership. So what's important to consider is, number one, when you look at a scanner, obviously I think NDX and DSG would be a great resource for you of trying to find the appropriate unit, but follow the manufacturer's instructions for the scanning techniques, determine the indications. Certainly single tooth is very popular, all the way to doing full arches. Define the margins, because you need to visualize the margins in order to get accurate digital impressions. And then isolation, of course, is required to properly expose those margins so you can capture them in a visual format. And the techniques today can be used in a variety of sessions. These are a workflow from a study that we conducted with Dr. John Sorensen. It utilized basically an indirect approach. He scanned the preparations, digitized them, sent them to our laboratory. We designed them, milled it out, sent it off to him, and then with the proper bonding techniques that we'll cover, provide a very beautiful and well-standing and reinforced restoration with the adhesive cementation protocol. So as we move forward, we look at material selections. We've gone through a whole renaissance of material selections, and I covered this in my first lecture. This is the third series, but I need to review it because you can't repeat enough to get the foundation, the background of what materials we're dealing with. Today, there's so many different choices relative to indirect restorations. And as we look at them, we have from lithium disilicates to resins to zirconia type of materials. We have translucent materials, high strength materials, and really balancing all these materials from a selection process is really important for a clinician to understand the selection process of what they want to utilize for final restoration. So if we look at our stratification, we've gone from composite materials, which are called hybrid ceramic materials. These are basically highly loaded, reinforced, particle-filled ceramic, composite type of restorations. We have the hybrid approach where we have, for example, a material from Vita that has a ceramic crystal structure penetrated with resin in between it. And then, of course, on the ceramic side, we have our weak feldspathic porcelains that are used on crown and bridge, our lucite reinforced materials. There were the earlier 90s, like Empress, that basically increased the crystal structure of the materials to provide some strength. The big boom was lithium disilicates like Emax and other materials today that provide a very high crystal structure of 70% and a higher strength. And then we have the zirconia materials, which are truly all crystal structure, 99.9% crystal structure, which provides one of the most strongest and durable materials we have in dentistry today. So as we move in the striation of materials, we've gone from optics to low strength to high strength materials that we can use in our practices today. And typically over the time, there was an element that the more translucent material, less strength that it had. We're rivaling this now with new technologies. We're actually increasing translucency and strength and making those materials work for us in clinical settings. So again, with the opportunity of doing indirect restorations, here we have the hybrid ceramic materials like enamic, where they're resin infiltrated and penetrated of the crystal structure. Here we have preparations, two-fold crowns, cementations, again, accordingly. Now, we look at these materials, we just want to review again very quickly, but we use two factors of evaluation for these materials. We use biaxial flexural strength and fracture toughness. And these are two values that you'll see when you relate to as far as comparing different materials. It's important to know because it relates to the survival rate and the predictability of success in a clinical setting with these materials. And when you read in the literature, certainly you want to be familiar with these properties so you can make your own decisions accordingly. So here we're looking at biaxial flexural strength. So as you can see here, they're discs of material that are loaded over time, and we value the comparatives that we have as far as related to those types of materials. Excuse me here when I move this over here relative to the slides. And what we can see here is that basically from a biaxial flexural strain, where you take a disc of material, you load it to a fracture rate. If we look at the composite materials that we have here on the left, TetraCAD, Lava Ultimate, Cerasmart, Paradigm, composite-based materials called hybrid ceramic materials, we're in the 200s. Enamic, which is a ceramic structure infiltrated with resin, about 180. Empress, a lucite reinforced material, about 180 also. And then we get to the lithium disilicate materials in a range from the 250s to mid 300s all the way up to 570 for Emax as a reinforced ceramic material. These were very exciting developments because the reinforcement of crystal structure increased the strength of these types of materials. The second property, which is becoming more and more popular from ceramic engineers because it really measures the resistance to crack propagation. And crack propagation is what induces failure clinically for this matter. So if we have a contact area, basically a functional area that's hitting, we have too high of occlusion, excursive forces, whatever, it may initiate a crack and propagate this micro crack can then expand with the hydrolysis of the materials, creating a fracture of the material.
One moment, please. We do have somebody's microphone unmuted.
We're going to adjust fire and continue throwing missiles at it until
Somebody else has a microphone open.
Yep. Bear with me. Oh, they're muted. Thank you.
Thank you. So anyway, so relative to this fracture, crack propagation is what's called fracture toughness, a very relevant process where we induce a crack and we measure the resistance to the fracture of the material. Here we have again the same discs relative to the fracture properties that we're inducing on it. And you can see here going from composites to a hybrid material to Empress, which is a lucite reinforced ceramic, all the way up to the lithium disilicate materials. So we range from 2.75 all the way down to about 1.28. So if we look at those comparisons again, the higher the fracture toughness, the better. Resin materials, which yield and bend about 1.3 to 1.7. Enamic at about 1.6. Empress, a lucite reinforced ceramic, about 1.2. And then some of the lucite lithium disilicate materials, Celtra Fired, Nice at about 1.8, and then Emax at 2.75. So these are very important properties to remember. So again, from the Emax properties of lithium disilicate, we had about 500 to 600 on fracture toughness and 2.75 relative, on flexural strength and 2.75 on fracture toughness. Now, as we move up the ladder, we want to talk about zirconia because we talk about the popularity of glass ceramics, and certainly lithium disilicates are very, very popular materials today, especially for aesthetic restorations. But it moves to the most strongest material, we move to zirconia. And there are thousands of different zirconias now available today, but not only are they stronger and the strongest of all the ceramic materials that we have, again, based on that property where they're 99.9% crystal structure in the material, so there's no free glass matrix in the material whatsoever relatively. So when we talk about zirconia, we just want to keep in mind, and this is a very important factor as we learn, is that today, and especially because most clinicians just prescribe a zirconia and your laboratory partner is the expert who can provide you information on that, but not all zirconias are equal. We had the traditional 3Y materials, which are the high strength zirconias, and today we've moved into a new generation of 4 and 5Y aesthetic zirconias that are more translucent, have less crystal structure, and therefore do not have the same properties as the traditional 3Y. So we're going to go through this in a little bit of detail here so we have a good understanding and description of the materials. But again, remembering that zirconia is not equal to all zirconias. There are different categories of zirconias, and we'll cover that here at this time. So basically, from a translucency standpoint, we have two different types of, actually 3 different types of zirconias available. 2 general categories. We have monochromatic, which are solid pucks that the laboratory mills out the restorations from. And these can be white, where they're infiltrated, or they can be pre-colored. And then we have multi-layered, the new aesthetic type of materials, where we have materials that are a certain chemistry, all multi-chromatic, but multi-layered at the same time, but of one material, just with different shading. And today, some of the new materials that are coming out are multi-layered combi, meaning they start out with a very strong core structure, but they move to a weaker, higher translucency material, and we call these multi-layered combi. So we'll cover this in a second here. Zirconia is a very unique material because it's balanced on a crystal structure that is a neutral self-healing property, which is called the tetragonal phase of the material. So if we shift the materials and we utilize them in this tetragonal phase, it provides the most self-healing, strongest crystal structure relative to the dynamics of the material. What's happened over time as we looked for more translucency in the zirconia material, we started adding cubic zirconia to the tetragonal phase. And the issue is that the more cubic material that we add, the higher the translucency, but it weakens the crystal structure of the zirconia material. So today in the marketplace, with the evolution of time, we started with the most stable material, which is 100% tetragonal. It's called 3Y zirconia, which is basically with the amount of yttria established in the material, is that basically this is the strongest, most durable zirconia. Manufacturers started playing around and utilizing terms like aesthetic on it. So we have a prime aesthetic, there's a Biaxial aesthetic, an Antura material, Argent and others also have these types of materials. And basically by adding the cubic zirconia, we increase the translucency, but at the same time also weaken the material. So the point we're trying to make here is that when you order zirconia, be familiar with what you're ordering and what the laboratory is delivering. Develop a partnership with the laboratory, because your indications may be different and how you handle those materials may be different, also related to the success of your restorations. Okay, so we have 3Y, 4Y, and 5Y. 3Y is the most opaque. It's the strongest of all of them. And then the 4Y has more translucency. And then the 5Y has more translucency, but again, weaker properties. So if we look at, try to remember what we talked about before, we said Emax had about 500 to 600 flexural strength relative to biaxial flexural strength. Actually, if you look here, then the traditional zirconias, the 3Y, has up to 1200 megapascals of flexural strength. So more than double the strength of an Emax restoration on a 3Y material. When we move to the 4Y, when we try to get as far as more translucency in this material, the 4Y materials drop to about 850. And then some of the most purest zirconias from aesthetic standpoint are at 650. So very comparable to like a lithium disilicate. And we see the same comparisons at, for example, with the fracture toughness, where we have the highest fracture toughness. So Emax was about 275 for fracture toughness. Here we have a value of 5 on the 3Y material, so a very fracture resistant material. As soon as we start adding the cubic zirconia, we go to 3.3 and 2.3. So really, again, a balance of those properties. What's important about that is real critically is how we prepare the teeth and what we can utilize relative to thickness of support of the materials. And if you can see here at the bottom of the chart, we talk about crown preparations. With a 3Y, we recommend that you have at least a half decent prep, but if you're restricted on thickness or whatever, you can get down to about 0.6 on the posterior of a 3Y material. However, if you did that in a 4Y material, the material would crack. So we need more thickness of a 4Y material, about 1 millimeter thickness, and for the 5Y, we need about 1.25. So very importantly is the preparation design needs to be guided related to what material you're choosing and how you prescribe it accordingly. So let's take a look at some of these materials here. And what we have is some traditional materials. So as when I'm looking at the chart here, if you look from left to right, We have the Zircad MO, which is a very traditional 3Y material at about 1200. We move into the LT and the MT, which are starting and moving in a blending of 4Y materials. So they drop down to about 800. We have another one, next CRS, which is a 3Y material. The T is again a combination of that. And the plus drops into about the 4Y material, the next CR plus. Bruxier HT, again, a 3Y material. As we get into shading of it, it moves into the 4Y material, drops down to about 1100. And the Bruxier anterior, which is a 5Y material, you can see is below 600. So knowing which brand you use, which material you use is very critical to the success of that final restoration. So here we're taking a look of showing the importance of a 3Y material. This is a 3Y material at 0.5 millimeter of thickness, conventionally cemented, and the load to fracture of this material is almost 4 times what a bonded lithium disilicate would be for that matter. So again, a very significant resistance to fracture of these types of materials. So here we look as far as in load to fracture of the material. So we basically made crowns. We took them in the lab. We did bond them in place, and then we loaded them. And as far as trying to break the types of materials, so you can see here, moving left to right, we have lucite reinforced ceramic called Empress, which has about 40% crystal structure. It broke over 2000. We had Emax, which is a lithium disilicate, about 70% crystal structure. It broke about 4000. And then we had a 4Y material Cubex X2. We have a 5Y Katana UTML, which broke at about 3000. We had a 4Y STML, which broke at about 4000. This is a new material, a multi, again, a blend that I talked about before. It's a 4Y material, so it's between 4 and 5. And then we have the new combi material, which is a 3Y material with a 5Y overlay, and it went over 6,000. And then we can see here that the purest 3Y material, pure 3Y material, gave the most strongest results related to fracturing, load to fracture of the materials accordingly. So again, what you choose and what you utilize provides the reinforcement of that final restoration. So just look at some of these cases. Again, many choices in zirconia. As I mentioned, Katana comes in monochromatic, basically solid pucks, and can be in shaded or pre-shaded, unshaded or pre-shaded type of materials. And basically the technician would fabricate the restoration. If it was in a white, they would infiltrate it with stains and fire the restoration, or they could surface characterize a pre-shaded restoration as well. The new move with the aesthetic movement is into multi-layered type of restorations. And we have multi-chromatic, that's one material that basically has different shading. So it has the dentin, body, and incisal shading. And then, as I mentioned before, some of the new combi materials, like our Zircad Prime, they utilize different chemistries. So we have the foundation, which is a 3Y, the density of the dentin, the coloring in the foundation of the restoration, and then the translucency of a 5Y that can be adjusted and milled by the laboratory accordingly. So this shows you again some of the difference. We have basically a Neapolitan look here with the multi-chromatic. They're one materials just with different shading. And then if you look at the right, that's the combi material like the Zircad Prime. And it's basically a blending material where we fabricate with a solid 3Y and then go through a blending process and a transitional up to a 5Y material to increase the optics of that material accordingly. So again, showing you some of the strengths we talked about as far as translucency. The 4Ys or the 3Ys the 5Ys and the 4Ys have the most translucency. And if you look at this profile here, it's very clear. You go from a 3Y, the MLHT at 1125, the STML, which is a 4Y at 748, and the UTMLs drop to about 557. And cross relationship, again, the higher the strength, the higher the density of the crystal structures, they're more opaque to more translucent with the other materials. So again, clinical judgment is related to the need of the final restoration. And these are just some cases showing you here again with the Zircad empty multi. This is a 4Y blended material. And you can see the transitional zone of the incisal versus the body of the material. And then again, this is the empty multi, some of the creations even posterior. So you've got a real translucent incisal with the body material. And then this is the technology that we're getting to the combi zirconias, where we actually blend the material, basically starting with a bottom as a 3Y powder, going through a sequential, mixing the materials in a transitional zone and building into the 5Y materials accordingly. So these are some of the high-end type of restorations you can see here with these type of restorations. Again, variety of application. Single crowns have provided a very high aesthetic result in the anterior, and certainly can be used in a variety of applications from single units, full mouth reconstructions. And again, very popular today is using these materials for implant fixed restoration. So again, utilizing solid structure of materials that have the 3Y strength with some of the aesthetics of the 4 or 5Y can provide a very strong element of benefit in these clinical cases. Okay, so we covered a highlight of where we are with materials. Let's talk about preparation design, and we touched on that accordingly. And so tooth preparation is very essential relative to the success of a restoration. So we choose materials. We can choose weaker materials, such as feldspathic porcelains, lucite materials, lithium disilicate materials that are stronger, of course, all the way to zirconia restoration. So our preparation design will relate to what material we want to use and how we want to use it accordingly. So again, some of the elements that are real critical to glass ceramic materials, whether zirconia or to lithium disilicate restorations, is to make sure that we have internal rounded line angles. These materials are still glass, and important to have rounded angles. The benefit, of course, is the fact is that the machines that mill these restorations out can't go into sharp edges. So if you have a very sharp edge, the burr can't fit in there and basically will hollow out your restoration. So that's a problem. The other factor is we want to provide enough thickness to the material, depending on the material we're using. And then typically we define them with a defined margin. So a deep chamfer or a shoulder preparation with very clearly defined margins, so the instrumentation can clearly fabricate those restorations. Now, the one thing I want to note is that this is a really important criteria, especially for lithium disilicates and for the 4Y and the 5Y. When dealing with the 3Y, which is a very tough material, we can have more forgiveness and more of a traditional crown and bridge margin on those areas, because they can be milled down to about 0.5 with the 3Y material because of its strength and edge strength accordingly. So again, as I mentioned, we don't want to have sharp line angles. We want to have rounded line angles, thinking not only from the preparation design, but what can the machine fabricate for us accordingly. And as you can see here, some of the burrs that come in, some are rounded, some are flat shaped. But if we go through and try to create that, basically you're going to create a divot in an open space related to the restoration. So that's not a good thing. And also we can compromise it because we can thin out the restoration, create a weakening of the restoration and compromise the thickness of those restorations. So rounded line angles are very critical to successful restorations overall. This is showing you the rounded line angles that we can. Again, there's a variety of different kits. There's a number of manufacturers. We work with a number of them. I'm not endorsing anybody for that matter, but Brasseler is certainly a popular name, and Axis and some of the other ones that are available today provide a number of different kits which can be used for depth cuts to establish the proper planes relative to the reduction of the restoration. So basically, you would use the depth reduction burrs accordingly for veneers or anterior crowns, and then connect the lines accordingly. And basically, again, bulk reduction, refining and smoothing them out, making sure that we have round internal line angles, and refining the margins is very critical with these types of preparation designs. And the same thing again for posterior restorations. There are a number of different depth cutting accessory diamonds available, again, for basically reducing them. Typically, we reduce relative to about 1.5 on the occlusal relative to posterior restoration with glass ceramics. With 3Y, with 3Y, we're down to about 0.6 minimal. It's not a goal to cut a prep at 0.6. I'm just saying get away with 0.6, but if you can do 0.8 to a millimeter, that certainly allows for a better, stronger restoration overall. And then with the 4Y, we said we go to 1 millimeter, and then with the 5Y, at least 1.25, if not more, relative to reductions. So again, depending on what material you have, the reductions certainly have to be utilized accordingly. And then for adhesive protocols, there's a difference between conventional cementation that doesn't reinforce the restoration to adhesive protocols. So for example, on glass ceramics like lithium disilicate, like EMAX, if we're conventionally cementing a posterior restoration, we should have 1.5 millimeters reduction. On the other hand, if we're bonding in place, either with a self-adhesive or a total adhesive cementation protocol, we can get away with 1 millimeter reduction in those areas. So let's just briefly take a look at some of the elements. We want to have basically rounded line angles, a draw, of course, sharp margins so we can facilitate, the machine can visualize it from our scanning or impression techniques and can actually mill the margins accordingly. If we have an adhesive crown for lithium disilicate type of restorations, we can bond them in and have a millimeter in place here for that matter. And then if we are using, for example, conventional cemented restorations, of course, then we would need 1.5, or if we're doing bridges, we need larger support relative to bridges accordingly for these areas. So adhesives like an occlusal tabletop, partial crowns, 3/4 crowns, a millimeter with bonding. And again, if we don't bond, then we have to go thicker related to those applications. So that's sort of repeating what we said before. If we're in the bonding category, we can reduce a millimeter. If we're going to conventional cementation, then it's about 1.25 relative to the reduction of these types of preparation guidelines. So now with the zirconia materials, 3Y and 4Y, same situations that we talked about. You can get down to 0.6 with a 3Y material. I don't recommend it. It's not ideal. I mean, cutting a 0.6 reduction preparation is very difficult to standardize. I'd aim for 0.8 to 1, but again, if you have a thin spot, you can get away with it because the durability of the material will be more forgiving. If you're in a 4Y material, then you have to have a millimeter, and a 5Y material, you should go to 1.25 relative to posterior reduction. Those are some of the principles we just discussed. And this is now looking at some of the 3Y and 5Y materials that we have, their combinations. Similar principles apply, millimeter reduction, and then again, making sure that we follow the proper protocols accordingly. Okay, so those are the practical principles. So knowing what material you choose is very critical, and then relating to the material, the preparation guideline follows accordingly. And if you work with your laboratory, they work with all the manufacturers. Everybody has prep guidelines related to the material. So there are tools, either can be electronically distributed to you or charts and handouts accordingly to facilitate some of the balancing that you have with the different materials that's a favor of the laboratory. So moving down our chain, let's talk about cementation protocols. So again, we have the different materials that we use, and it varies on the type of material that we pick accordingly. So there's different categories of cements. We have adhesive cements, we have self-adhesive cements, and we have conventional cements. So adhesive means a total bonding where we prep the dentin, we prep the restoration, and we can loop them in and bond them in accordingly in a very, very tight fashion with a high reinforcement. Newer category of cements, they've been around for a while, but becoming more and more popular, like Reliax Unisem, Maxem, SpeedSem Plus is our material, GSem and others. These are materials that basically have a primer built into the cement. So they provide not as high of a bond as the total adhesive cements, but they do provide a bond and a decent one in different situations. So you basically, if you have a moderate retentive prep, you can skip maybe the adhesive steps accordingly and use a self-adhesive cement to retain a crown, either zirconia or glass ceramic accordingly. And then bottom line, for ease of use, where you have retentive preparations and high strength materials, you can utilize conventional cements accordingly. And typically these today are the resin modified glass ionomer materials. We have a new one, Zircad Sem, Relax Luting, Fuji, and others that are available for this category. So let's take a look at these indications. So what type of restoration we place is a very important factor. What restorative material will be used to create the restoration? So are we going to use a composite hybrid ceramic resin? Or are we going to use a glass ceramic like lithium disilicate, feldspathic, or lucite? Or are we going to use a high strength oxide ceramic material like zirconia? Alumina was around for a while, not as popular today. And of course, metal restorations is an option also. And then we have to look at what is the condition of the preparation. Is it a tapered preparation? Is it a retentive preparation? Do we have good isolation? Do we have bad isolation? What are the circumstances? So, I mean, if you have a preparation that is difficult to isolate, it's very difficult to do a total adhesive cementation. On the other hand, if you have a proper retentive preparation, you may not have to have an adhesive cementation protocol. You could cement a high strength ceramic with a traditional conventional cement and have a beautiful result accordingly. So we'll look at these variables as we move forward. So again, looking at the type of material, are we using a translucent material like a lithium disilicate, or are we using an opaque material like zirconium oxide, or a metal material, which is very strong to relate how we'll bond those restorations, because some of these cements can be dual cured and other ones light cured to cement the properties accordingly. And then also we have different translucencies of different factors of cements. Here we have a cross section of a variety of different glass ceramic materials, and you can see that based on the chemistry of the materials, they have different translucency properties that allow us to properly bond those restorations in accordingly. So let's dive further into the cement protocol. So we have conventional cements versus adhesive cements, and then high strength materials versus low strength materials. Those are our criteria we have to think about when we're selecting a cementation protocol. So this is a very good demonstration here. Basically, it's a loading study where we took a weak ceramic with a weak cement. We got a 600 on a loading there. We took a weak ceramic with a high strength cement. We doubled it to about 1200. We took a high strength material like Emax and a weak cement, and you could see we went to about 2000. And then we went to a high strength ceramic and a high strength composite cement, and we went to about 2700. So again, what we use and what we use for cementation plays a very critical factor on the success of that final restoration. And I want to keep you in mind, as far as there was a previous slide or video that I showed you of the same study where we had a zirconia at 0.5 with conventional cement, and the value was at 3800. So 600 for a weak, 1100, 1200 roughly for weak and strong. Strong and weak was ceramic was about 2000, and then the strong ceramic and the strong cement at 2700. And if we use zirconia in that fashion, then it's even higher. So again, balancing the properties of cement. Not only the material makes a proper result to it, but the cementation protocol has a significant influence on that direction. So running through again further, looking at the variables that we have here, we talk about interface dynamics. And basically we have to look at two surfaces, how we're going to treat them and how we're going to utilize them. And so we have the restoration, the inside of the restoration, which is the indirect restoration. Then we have the two structure. And how are we going to link those together through what mechanism with the cement to bond them accordingly and provide a proper seal is a real critical factor. So we're going to talk and focus on these interface dynamics, the surface treatment of the restoration, and the surface treatment of the tooth, and how we link them together with the cementation protocol. So first, we're going to look at the restorative materials and the surface treatments, and then we'll look at the tooth. So basically on the restorative side, we could have a composite-based crown, like a Lava Ultimate or something of this sort, or enamic. Basically, it's hard to roughen them up material. So basically, you create a micromechanical retention through sandblasting. The glass ceramic materials like feldspathic porcelain and lithium disilicate and lucite reinforced require a hydrofluoric etching. The hydrofluoric etching in the laboratory or chair side creates a micromechanical retentive pattern for the restoration. And then for the zirconia, we lightly air abrade it And we use a chemical primer called a metal zirconia primer. There are a number of them. Ours is Monobond Plus, and there's a number of them from Carrari and Bisco and other ones that basically are multifaceted chemistry where they're primers and create MDP bonds with the crystal structure of the zirconia and the metal oxides as well to provide a very, very strong bond in these restorations. So in priming the restoration, we either hydrofluorically etch or we prime chemically some of the high strength materials, or we sandblast the weaker resin type of materials. On the tooth, on the right-hand side of the slide, on conventional cements, we really just clean the tooth. We can pumice it, clean it up, but we really don't treat the tooth because it's going to be basically conventionally cemented. Same thing for self-adhesive cements, because they have a primer built in the cements that can penetrate into the tooth structure. And then on the adhesive cements, we use our total etch or typical type of adhesive procedures. We can total etch and rinse, or we can selectively etch only the enamel and not the dentin, or we can do a self-etch pattern where we can bond the entire restoration to the tooth structure. Okay, so those are the areas: interface dynamics, tooth, and this restoration. And then we can talk about the adhesive cements, cementation protocol here for adhesive. We're going to bond the restoration in place. So we have a clean tooth structure. We're going to do a try-in. There are try-in pastes available for the composite resin cements. This is our Verlink try-in material. We want to make sure that after try-in, we clean the restoration, and we have the ability of using these phosphate protein cleaners, like called IvoClean, and there are other materials available for this process. A very viable material that provides a very clean surface for the internal aspects of the restoration. We then hydrofluorically etch the restorations to make sure that they are adequate with proper priming so that we create this crystal structure in the glass ceramic material. And then we put a primer on there. These Monobond Plus and these other multifaceted glass ceramic metal primers provide a very strong chemical link. It's like the old silings, but much more broader in chemistry application. So we put on the primers, we let it react 60 seconds, and we dry it with air to create this uniform bond with the material overall. So we've primed the restoration. On the tooth structure, we scrub the tooth with our universal adhesive. In our case, we're using Adhese Universal. So we scrub it for about 15-20 seconds, create a micromechanical penetration and hybridization of the dentin. And then we air dry it and basically light cure it accordingly. We're working now on some of the dual cure versions, but basically by air drying it and bonding it in place, we create a very strong pre-sealed bond of the restoration. Here we're curing it, 10 seconds. And then we proceed with basically loading the restoration and seating it accordingly. So we've had interface dynamics. The tooth's been treated, the restoration's been treated. We load the restoration with our dual cure resin cement. We seat it. We cure it in a wave format. So we tack cure it, carve off the excess, and then can basically go ahead as far as in final polymerization of the restoration. So this is a very popular technique. We're showing you here the wave technique. We basically take a high strength, a light, a curing light, wave it, gel it up, and we put it in the gel phase so we can basically peel off the excess cement and keep a clean margin, and then basically make sure that we don't have any residual in the interproximal areas, and clean up the restoration, then go for final polymerization. So just showing the quadrant technique also from both areas. You're waving the technique and basically gelling it up, peeling it off, and then final polymerization accordingly. So here we are cleaning it up, peeling it off, and basically by doing this wave technique, it's in a rubberized gel format, so it's easy to peel off before final full polymerization. And then we can go through final polymerization, final curing, holding the restoration in place, polishing, cementation, of course. And then we have a final cemented restoration. So again, that's total adhesive technology, which is used for glass ceramics, especially for anterior restorations, partial coverage, inlays and onlays, and for full crowns as well, depending on the clinical case as well. On self-adhesive cements, this is becoming very popular today. It's not as strong of a bond as the adhesive. Basically, you can get 30 megapascals for the total adhesive technique. We get about 15 to 17 for self-adhesive, but the benefit is its ease of use. There's no surface treatment to the tooth structure whatsoever. So what you'd have here is you'd have a crown prep. You basically have your cement. Let's take a look at it here. You try it in. Basically, you'd clean it out accordingly with the IvoClean that we mentioned before. Let that rinse off the proteins and the excess from the saliva. Surface treatment of the tooth is not necessary because the primers are built into the cement. We bleed the syringe first, then load the restoration, seat it down, and then carve it off again with the wave technique. So again, interface dynamics to make sure that we have the proper sealing of the restoration. Very popular today. Again, it's an intermediate step. I wouldn't do it on partial coverage or on TP preps, but if you have a decent retentive preparation, full crown, it's certainly a very viable technique because it gives you the strength and the flexibility and the ease of use of using these types of restorations. So again, easy cleanup, carving off the excess, and then basically final cementation, curing it fully to make sure we have full polymerization and completion of the restoration. Okay. And the final, as far as of looking at glass ceramics, as far as, of the modification of these on glass ceramics, the important thing is that we would use the primer for this because we need the chemical reaction with the ceramic accordingly. So using Monobond Plus in this case is a very important criteria to make sure that we get the priming action for the interface of the restoration. So if we look at the techniques, hydrofluoric etching, air drying, then we're applying the Monobond Plus, the primer, to make sure that we facilitate the priming and the sealing of the restoration. We then load up the cement, we seat the cement, we wave it, carve off the excess, and then final polymerization and have the final restoration. So again, the utilization of self-curing cements, self-adhesive, self-curing cements is very popular. And then finally, very importantly, is on the conventional cements. These are one of the most popular cements available today. These are for full crown retentive preparations. Again, very popular technique. Our material is called Zircad-Sem, but Relax Luting, Fuji-Sem, and some of the others are certainly popular in this category. So we clean the preparation, sandblast the restoration, clean it off, and now you're just going to apply the Zircad cement, inserting it, letting it set up, tack it for 5 to 10 seconds per segment as we did, cleaning it up, and then let the set time and then finish and polish and complete the restoration. So the most easiest and most user-friendly of all the cements, again, but the most weakest bond of basically retentiveness. So we go from 30s for total adhesive, we go for 15 roughly for self-adhesive, and the resin ionomers have a small bond, but it's between 4 and 6. So basically a light adhesive reaction on that type of area. So summarizing our protocols, again, very importantly is to understand what material we're using, how to use it accordingly, priming the restoration, priming the tooth structure, and relating it to the material we're using with the appropriate cement to lute them in and bond them in together to have a very good seal on the final restorations. Last topic quickly, I'm close to my time here, but as far as I want to just talk about as far as in the end here, as far as finishing, polishing, which is very critical. So we've cemented the restorations, we've chosen the materials, we have the ideal preparations, and then relative to finishing techniques. The glass ceramics and zirconia materials are very sensitive because they are glass. And there's two factors. One is not to induce stress fractures in the materials by overheating them. And the second point is not to leave a rough surface where it becomes abrasive to opposing tooth structure. So making sure that we have proper finishing or glazing is very important. Polishing and finishing is actually more important than glazing in many situations because it provides the ideal surface, especially after the glaze wears off for these restorations. So it's very important to look at either extraoral or intraoral adjustments. If we adjust a restoration, either extraorally or intraorally, it's very important to go back and provide a very fine finish to that material so it has a glassy, smooth interface for the viability of functional areas and especially in contact areas overall. So we want to use very fine diamonds, high copious water spray, and then finish them off with a sequence of high high fine polishers to provide that glassy surface accordingly. And this is a study just showing some of the implications that can occur from those areas. What we have is, let's look at the opposing wear of what happens if we have a rough surface opposing the wear of a two structure. So here we have basically in the first line item, we have an A lithium, which is adjusted lithium disilicate. And then we have a polished surface of lithium disilicate. And then we have a glazed surface of lithium disilicate. So in the lithium disilicates, if you adjust it and just put it in the mouth, you create the roughest pattern of wear to the opposing two structures. It can be very catastrophic. If you polish it, you basically cut it in half. So polishing is a very significant factor. And then the ideal would be polish and glazing, but sometimes from a laboratory perspective, it's quicker just to put a glaze on it. And so the glaze you saw is about 0.47. On zirconia, same situation, adjusted, very rough. If we polished it, we cut it down in half. And actually in glazing, because the glaze wore off here and it was unpolished underneath, we achieved a higher wear pattern on that overall. So again, adjusting and polishing is very critical to the success of these final restorations. So let's take a look at a couple of cases here. One is, this is a zirconia and lithium disilicates. Again, on the zirconia, we use water spray, very, very fine diamonds. We adjust the restorations as necessary. We adjust the anatomy. Then there are a number of different polishers available to us. Dialite is one of the leading brands as far as in providing high shine for glass ceramic materials. We can adjust it with the grinder, refine it with the medium grinder, and then go through the sequence from medium fine, the green materials, to the orange, which is the fine material, and then providing a very nice fine polished surface that can be functional and dynamic in the functional areas of the oral environment. Same thing on lithium disilicate. We use the grinder, the pre-polish wheel, the fines, and then create basically a beautiful crown. So it's very important to go back. If we adjust these restorations, high speed, fine diamonds, copious water, and then make sure that we use the rubber assortments that we can to repolish these systems back in place. And this can show you, again, these are polished restorations, again, some of the beauty that can be achieved through these elements of application. The other factor we want to look at is what happens if we have to adjust or actually penetrate and do endo-access. So again, this is a study that we conducted a few years ago. It was published in the IEDR, the annual session. Again, if we have endo-access, we did a study here looking at different areas, and what came out was that, again, the coarser the diamond, the more damage it created to the restoration. So basically, we want to use fine diamonds, high copious water spray, high speed to penetrate these areas, and can use some of the different areas. So here we have a 30 micron, a 60 micron, 126 micron, and a coarse micron. And on the right side, you can see some of the peripheral damage that occurred from these types of restorations. And then in a loading study where we went and basically loaded these materials to fracture, you can see basically an unpolished crown at 3000. When we did an axis opening with a fine diamond of 30 microns and bonded a filling in there, it actually went up in strength. And then you can see consecutively the degradation when we used coarser type of diamonds for creating these axis holes accordingly for the axis preparations for these areas. So again, fine diamonds, copious water spray is the best situation in adjusting and also penetrating some of these restorations. I'm gonna jump through this. And then once we're done, the important part is to use these extraoral and intraoral adjustments. Polishing is very critical. I mentioned DiaShine. We have a system called OptiGloss. Again, a two-sequence pre-polisher and high shine polishers with all the different dimensions. And it's important to go through the sequence to create that final luster for the restorations. I'm going to jump ahead here because I want to just come up to the final. So again, summary, high speed, copious water, fine grit, and polishing afterwards to adjust the final restorations. And the last topic I want to just talk about is the maintenance of these restorations. We've produced very highly aesthetic, beautiful glass ceramic materials and restorations for our patients, making sure the periodontal health is really integral. is important. And there are a number of different varnishes available today for post-maintenance of these restorations. And professional care is very important to make sure that the integrity of the restoration is proper, as well as the oral environment, the health of the tissue surrounding the restorations. And so there are a number of different materials available. There's fluoride varnishes. We have two. One's a chlorhexidine-based material called Cervatec Plus, and the other one's Cervatec F, which is a fluoride chlorhexidine varnish as well. Choosing either one is appropriate, but basically providing this as an after treatment is very critical to ensure successful maintenance result of these types of restorations. Because you put in these restorations, you want to make sure that the hygiene is impeccable, as well as the maintenance factor of these restorations. So this improves gingival health overall surrounding the restorations. Basically, what you would do is a recommendation is to use this on a routine basis by the ADA's clinical prevention practice guidelines. You paint it onto the margins of the restoration, let it polymerize, and basically it maintains itself to releasing the chemicals for providing the benefit accordingly. It can be used on implants, on restorations, a variety of different surfaces, antimicrobial, and a periodontal enhancement supplement. So this is the step-by-step. We clean, we dry, we apply, let it air dry, and then basically let the material provide the benefit that it can. And the other varnish we have is a combination chlorhexidine and then also a fluoride material called Cervatec Plus, and provides a good fluoride benefit relative to the application. It seals the tubules, also as a desensitizer. And then again, the sequence here is you clean it, you prophy it, dry them, apply the Cervatec F, let the varnish set for the appropriate time, and then let the material provide a benefit. So maintenance of restorations is a very critical factor as well. At this point, I want to end, as I've gone about 10 minutes over my lecture, so we're at the full hour here. We're very excited as far as of what we have as far as of total aspect of the restorations. I think tonight I've covered a variety of different topics. We talked about the excitement of new technologies in all ceramic restorations, the ability of fabricating these restorations through new digital processes, working with your laboratory to select the corresponding appropriate restorative materials. We have a variety to choose from glass ceramics, lithium disilicates, the zirconia restorations, 3Y, 4Y, 5Y, following the proper applications of these materials for success with proper preparation and cementation protocols. And then finally, once we have beautiful restorations, how do we maintain them and provide a long-term success for our patients? So with that, I want to thank the audience for the attention tonight. It's been a real pleasure. And